Hello everyone, this is Dr. Rajarajan Sivaraj. I'm a Principal Technical Architect with Mavenir, and I'm here to talk about applying scalable and practical machine learning for real-time programmable optimization in 5G cellular networks. In this talk, we will cover some recent advancements in 5G architectures and use cases that render machine learning practical, realizable, and scalable. So let's start with the introduction. We reviewed the traditional mobile network architecture with the cellular radio access network or the RAN, core networking components, and the application layer components interoperate with each other using protocol and standards. The cellular RAN base station, called the Evolved Node B in LTE, has the network functions for the layers of the RAN protocol stack and radio head antennae for transmission via radio frequency signals. The user is connected to the cellular RAN base station via the wireless radio link, and then to the packet core network, which has the core networking components like the serving gateway, packet gateway, mobility management entity, etc., and then connected all the way to the application server through the internet backbone. The application server can be something like Netflix, Amazon, Facebook, etc., and they have protocols like TCP, UDP, QUIC in order to transmit streams of data to the subscribed user equipment. Now, the traditional cellular RAN in the mobile network is a monolithic building block. What does it mean? It means that the cellular RAN baseband unit as well as the radio heads are integrated in the same physical cell site. The baseband unit takes care of the network functions of the protocol stack, and the radio frequency signals are transmitted via the antennae in the radio units. Now, each cell site has a limited range of coverage. And in order to have a ubiquitous and pervasive coverage across a wide geographic region, it is required to deploy tens of thousands of cell sites and hence tens of thousands of baseband units. And hence it's a costly exercise. It is not a cost-effective exercise. Now, the baseband units are also implemented as proprietary network functions by proprietary software that is built on proprietary hardware. There is no notion of logical nodes within the baseband, and hence the proprietary nature of implementation and the monolithic building block pose significant challenges to existence of multi-vendor compatibility. 5G introduces the notion of disaggregated RAN. What is meant by disaggregated RAN? The 5G base station, called the next generation Node B, has a split BPU. The BPU is split into a centralized unit called the CU, and one or more distributed units called the DU units. The DU units are connected to the radio units via the front hall. The centralized unit is further split into a control plane unit and one or more user plane units. Now, the CUCP of the control plane is connected to the user plane or CUUP through the E1 interface. The CUCP is connected to the DUs via the F1C, and the CUUPs are connected to the DUs via the F1U interfaces. Now, what is the rationale behind the split architecture? The layers of the RAN protocol stack are mapped onto these individual logical nodes. For example, the RRC layer and the PDCP control plane layer of the RAN protocol stack are mapped onto the CUCP. CUUP is responsible for the SDAP and the PDCP layers. DU is responsible for the RLC, MAC, and upper PHY, and RU is responsible for the lower PHY or for RF transmission. Now, this split architecture is scalable and it is flexible in terms of implementation, and it supports the time granularities required for different time sensitivities for different processing operations. For example, the network functions of the CU requires non-real-time, typically requires near real-time granularities, ranging from tens of milliseconds to the order of units of seconds, while the network functions in the DUs require real-time granularities, typically ranging in the order of units of milliseconds to tens of milliseconds. Now, if they're implemented in two different hardware, then the implementation can be even more flexible, because these hardware units can have different computational resources, can have different capabilities, and hence can support different time granularities for these network functions, as opposed to dumping them all together within a single hardware. What is virtualized RAN? So the network functions can be moved from proprietary hardware to commercial off-the-shelf cloud platforms. Now, it is still a proprietary software implementation, but it has virtualized functions on the COTS, on the commercial off-the-shelf platform service. Now, the deployment is scalable and cost-effective because instead of deploying tens of thousands of baseband units in physical cell sites, you're migrating the network functions from these baseband units to a centralized cloud, and hence it can support it can support a very scalable implementation, and multiple baseband units can be migrated to the centralized cloud with flexible hardware and software implementations. Now, there is a better coordination as a result of better load management across these baseband units, better sharing of computational and storage resources, and these coordinations improve performance optimization for meeting certain quality of service guarantees. So the logical split and the virtualized RAN architecture help in the scalable and flexible deployment of the baseband. The interfaces are proprietary. They are not necessarily open. The network functions are proprietary. The software implementation is proprietary. The remote radio unit hardware, that is also proprietary. Just that the network functions are deployed in a commercial off-the-shelf platform. So these still pose challenges to multi-vendor compatibility because of a lack of openness of these interfaces. So we move on to Open RAN. Open RAN will have open interfaces. So the baseband units support open interfaces and hence are prefixed by an O. It's called ORAN compatible baseband, and OCUCP, OCUUP, and the ODUs. So the interfaces are open. Similarly, the radio units are COTS-based hardware. They can be purchased from any RAN vendor, and the front hall interface is also open. So the interfaces are open. What about the network functions? The network functions are proprietary. So if the network functions are proprietary, how can you optimize the network functions of the RAN? So ORAN supports new interfaces one of them is called O1 interface. The baseband unit is connected to the service management and orchestration framework through this O1 interface. The SMO hosts a component called the non-real-time-RIC that has microservices to optimize RAN functions in the underlying RAN at non-real-time granularities. There is another interface called E2 interface standardized by ORAN. The baseband units are connected to a component called the near-real-time-RIC that has extensible microservices to optimize network functions of the protocol stack at near real-time granularities. And the interface is called E2. The non-real-time RIC and the near real-time RIC also communicate with each other via the A1 interface and also over the O1 interface. Now, these interfaces are open, and through microservices, third-party microservices that you can deploy in these RIC components, you can exercise some control actions back to the RAN to optimize the network functions. So this is the Open RAN architecture. And let's look at the flow between the hierarchical control loops of the Open RAN architecture. Now we have the Open RAN compatible baseband units, what we saw on the previous slide, and you have the Open RAN RIC components. Now, trace data is sent from these Open RAN compatible baseband units to the SMO via the O1 interface. This trace data includes both cell level traces as well as user level traces. Example of cell level traces are per cell spectrum utilization. Example of user level traces are average user RAN latency for a given session. Now, these traces are sent at non-real-time granularities, typically ranging in the order of units of seconds to units of minutes. And the SMO uses some machine learning and artificial intelligence-driven configuration management functions. So these configuration management functions exercise configuration back to the RAN, using which certain parameters in the underlying RAN can be optimized. Certain configuration parameters in the underlying RAN can be optimized. What are examples of that? For example, configuring the scheduler parameters of the MAC scheduler that sits in the ODU. This can be sent over the O1 interface. And similarly, configuring the periodicities at which user-specific data has to be reported to the SMO. This is another configuration that can be sent over step number 2. Now, using the data that the SMO receives in step number 1, the non-real-time RIC builds some machine learning and AI models based on offline training, and it basically sends some declarative policy guidance to the near real-time RIC. What is a declarative policy guidance? It basically enforces policies for the RAN optimization that is performed at the near real-time RIC. Some examples of declarative policy guidance includes predicting the RAN latency at the non-real-time RIC and offering guidance about the predicted latency to the near real-time RIC via the A1 interface. The second example for a policy guidance is setting objectives for optimization. For example, minimize the RAN latency for a group of users. That is another example for policy guidance. And then a cell level policy guidance is, maximize the throughput for a given cell subject to certain constraints. So all these are sent as policy guidance via the A1 interface. The near real-time RIC receives this policy guidance from the non-real-time RIC over A1 and also gets near real-time measurements from individual user-specific measurements from the underlying baseband units. Individual user-specific near real-time measurements from the baseband units are also sent via the E2 interface in step number 4. Now, these measurements contain user-specific RAN state information that are instantaneous based on the underlying channel conditions. For example, the user-specific buffer size, the amount of resources allocated to the user, what is the rate, modulation rate allocated to the user. All these are sent in step number 4. And then the near real-time RIC also implements machine learning models, also builds machine learning models based on training of the data set that it receives in step number 4 and the policy guidance it receives from step number 3. And these machine learning models are useful for optimizing the functions of the underlying RAN. So these machine learning models are used by the extensible microservices inside the near real-time RIC, which has virtualized network functions in order to optimize the functions of the RAN protocol stack in the underlying baseband units. Now, these decisions, these radio resource management decisions, optimization decisions, are communicated back to the RAN in step number 5 as control actions or as imperative policies. Now, step number 5 talks about imperative policies and step number 3 talks about declarative policies. What is an imperative policy? Imperative policy answers the question how. It specifically gives you guidance on the specific RAN operations that has to be performed by the underlying RAN, while step number 3, declarative policy, talks more about high-level objective intents and high-level policy guidance. Okay. And once the underlying RAN incorporates these optimization solutions from the non-real-time RIC and the near real-time RIC, it again feeds KPI traces to the SMO in step number 6. It's a repetition of step number 1, and the cycle follows. Now let's look at the use case of how we can optimize the operations of a cellular RAN using Open RAN architected components and using machine learning. We talk about the case of dual connectivity. What is dual connectivity? It is the initial mode of deployment of a 5G network. The user is connected to both the LTE radio, the LTE node B, as well as the 5G G node B. The user can access the 5G network if and only if he's connected to the LTE network, and that's why this deployment is called NSA, non-standalone deployment. The LTE node B is responsible for the control plane operations dealing with call connectivity and mobility, while the data plane is jointly handled by both the G node B as well as the LTE node B. Now, if the LTE node B were to alone handle data transmission, what happens is the PDCP layer of the LTE node B receives IP packets from the S gateway, and then it transmits the IP packets through the lower layers of the LTE to the user equipment. Now, this data barrier is called an LTE only barrier. Okay. Now, if the 5G G node B were to handle the data transmission, what happens? The 5G G node B receives IP packets from the S gateway, and it splits the IP packets between the 5G interface and the 4G interface. What it does is that it transmits a portion of these IP packets via the lower layers of the 5G RAN protocol stack all the way to the user, and it forwards the remaining portion of these and forwards the remaining IP packets over the X2 interface to the LTE node B. The RLC layer of the LTE node B receives these packets from the PDCP layer of the G node B and transmits them via the lower layers to the user equipment. Now, the control plane is exclusively handled by the LTE. It is the RRC layer of the LTE that talks to the mobility management entity and not the RRC layer of the NR. Now, we talk about latency here because our goal is to minimize RAN latency in this dual connected network. What is RAN latency? The time taken for an IP packet to be transmitted to a user equipment from the point of time the IP packet reached the G node B from the core network. This is called the RAN latency. This is called the user plane RAN latency. What are the components of user plane RAN latency? One is the queuing delay, the other is the contention delay, and the last one is the retransmission delay. We look at these delay components in subsequent slides. Now, this is a logical buffer for a user inside the G node B or the E node B. Now, let us assume that this buffer has about n packets queued inside the buffer. Now, when the n+1th packet is about to be transmitted to the user, it will have to wait up until all the n packets in front of it are successfully transmitted to the user. Now, the higher number, so the cumulative delay of all the n packets will typically impact the time at which the n+1 packet will be getting transmitted. Now, the queuing delay is higher when the network is heavily congested, or when the channel conditions of the user are poor, or when the arrival rate of IP packets is higher than the departure rate. The other delay component is called contention delay. So when the IP packet is ready for transmission to the user, it can get segmented into multiple PDU segments based on the conditions of the underlying network. And each of these PDU segments are transmitted in a time slot, and they need not be transmitted in consecutive time slots for the user. They can be transmitted in non-contiguous time slots, and the periodicities between any two successive time slots can also vary across segments. This also adds to the RAN latency. When there is heavy congestion in the network, this contention delay will be higher. The other delay is called retransmission delay. When a PDU is about to be transmitted to the user, but it's not successful in its attempt, there are multiple attempts which are tried for retransmitting the same PDU, and these retransmission attempts happen in different time slots, and these can also add to your RAN latency. And this retransmission is as a result of choice of poorer modulation rates for the user. Now, our goal is to typically minimize the RAN latency for an average IP packet. And how do we do that? Is by optimally splitting the IP packets across the G node B and the E node B, so that the average IP packet experiences minimal latency. And the user, as a result, also experiences minimal latency. We do this by leveraging the RIC components. So the non-real-time RIC is responsible for declarative policy guidance. What it does is that it gets the per UE and per cell measurements over the O1 interface, stores them in the data lakes, and develops offline machine learning models to determine policy guidance for the traffic split. The output is what is sent over the A1 interface. The output consists of policies to minimize RAN latencies for the user, and also predicts the RAN latency and offers the RAN latency as a guidance via the A1 interface. It will also have policies for traffic split. For example, minimum of 10% of traffic should be split on either interface. This is an example for a policy. And then the near real-time RIC is responsible for optimizing the network functions of the RAN protocol stack at near real-time granularities. Now, it gets policy guidance from the A1, and it also gets near real-time measurements from the E2, as we've seen in the previous slide. And what the near real-time RIC does is that it predicts user-specific growth of buffers inside the E node B and the G node B. If the E node B buffer is growing faster, then it will divert a significant chunk of traffic to the G node B and vice versa. So the growth of buffers is influential in deciding how the near real-time RIC should decide on splitting the traffic across the two interfaces. Now, the decisions made by the near real-time RIC are sent back via control actions over the E2 interface to the underlying baseband units. And these control actions will be how the traffic should be split and what should be the policies for the scheduler. For example, policies that dictate the PDU sizes for the user, the segmentation for the of the IP packet, how many resources have to be allocated, what rate has to be allocated to the user. These are all given as imperative policies, from the near real-time RIC to the underlying baseband units. Now let's look at some examples of how we can predict RAN latency from trace data in the non-real-time RIC. So the non-real-time RIC gets some of the following trace information from the underlying baseband units over the O1 interface. These include cell-wide information, cell-specific information such as the spectrum utilization of the cell, number of active connections within the cell, the bitrate served by the cell, and it can also include user-specific trace information. For example, what is the end-of-session latency for the user? What is the session throughput for the user? What is the average rate of what is the average modulation rate chosen for the user? What is the average resource allocation schedule for the user? Number of IP packets, retransmissions, and also users' channel conditions. Now, these are sent at non-real-time granularities to the non-real-time RIC. The non-real-time RIC can have some machine learning models like random forest regression or classification that can help predict the RAN latency. Even with coarse data set for these trace data, a machine learning model can give you a reasonably good precision score. And if these trace data are even more fine-grained, you can even get higher precision scores. So even with coarseness of data, you can get precision around F1 precision of around 0.6. Now, the machine learning training takes in the order of days across tens of base stations and hundreds of cells. And once the RAN latency is predicted, it is offered as guidance over the A1 interface, along with some enrichment information that talks about the impact factors of these input features, the details about the machine learning models, and also objective intents like minimizing the objective to minimize the RAN latency for a group of users. And also guidance on how traffic will have, like what is the minimum amount of traffic that should be split on either interface. And then what happens in the near real-time RIC is, apart from the A1 policy guidance that the near real-time RIC gets, it also gets some near real-time E2 measurements pertaining to the user. And these measurements are reflective of the instantaneous RAN state conditions of the user, instantaneous RAN state information about the user, which includes information about the buffering of the user at the E node B, G node B, buffer statistics, retransmission buffer statistics, rate allocation, resource allocation, quality of service, current packet split ratio, and again signaling measurements, etc. These are all UE-specific RAN state information based on the underlying channel conditions, instantaneous channel conditions, and these are sent at near real-time granularities. Now, the near real-time RIC can actually use some deep learning techniques like LSTM, etc., to predict the growth of the user's buffers in both the E node B and the G node B in near term. For example, in the next 10, 100 milliseconds, or in the next 1 second, what is the predicted growth of buffers for the user inside the E node B and the G node B? Now, the training for this prediction will typically involve tens of seconds to units of minutes worth of data. And then the near real-time RIC will also make optimization decisions, again by using some machine learning models, like, for example, decision tree-based reinforcement learning or Q learning, that decides whether a set of packets, a packet or a set of packets needs to be sent over the LTE interface or should it be sent over the NR interface. Now, once the near real-time RIC makes those decisions, these are sent back via control actions back to the underlying baseband units over the E2. The near real-time RIC can also make policy decisions about how the RLC layer, MAC layer should perform in terms of allocating resources, in terms of segmenting an IP packet into PDUs, and these policies are also sent via the E2 interface. Now, coming to the last part is we spoke about optimizing the cellular RAN using Open RAN technology. How can you optimize the performance of the end-to-end network using an Open RAN technology? Now, in addition to the Open RAN technology, we also talk about a network edge cloud platform. Now, the traditional networking components are interoperating with each other based on protocol and standards, and it is always the best effort service. In order to meet performance guarantees that are required for serving network slices, we basically build a layer of end-to-end intelligence, a programmable layer of end-to-end intelligence as a virtual layer on top of an underlying physical network. We make use of the RIC and the network edge cloud. How do we do that? The RIC platform talks to the cellular RAN and makes some intelligent predictions. These predictions are sent to a network edge cloud platform like Azure or Amazon EC2, etc. The network edge cloud platform has containerized microservices. Now, these containerized microservices map the predicted RAN KPIs to optimizing higher layer IP layer or application layer parameters. For example, the containerized microservices maps the predicted RAN throughput to video bitrate choices of optimal video bitrates, video resolution. Video resolution is based on the underlying throughput that the RAN is offering. And similarly, the containerized microservices will map the predicted RAN latency to IP packet sizes. Our results have shown that IP packet sizes impacts RAN latency by about 10%. So it maps on the predicted RAN latency to optimized IP packet sizes. Now the containerized microservices sends these higher layer optimization solutions as a guidance through REST APIs to the third-party servers like a VR server, video server, or AR server, which then can use these recommended values in terms of configuring their higher layer parameters, application and IP layer parameters. Like as you can see here, this is the traditional RAN that we spoke about, and then you have the RIC component, which has XApps that predicts RAN latency, RAN throughput, etc. And you also have the network edge cloud platform that has containerized microservices. Now, the RIC basically talks to the cellular RAN over the ORAN interfaces, and it predicts the throughput and predicts the latency. And this predicted information is sent via REST APIs, not through standardized interfaces, but through REST APIs to the containerized microservice inside the network edge cloud platform. The containerized microservices has, again, machine learning algorithms to map predicted RAN KPIs to higher layer parameters like predicted RAN throughput to optimized bitrate, video bitrate, predicted RAN latency to optimized IP packet sizes. And these optimization solutions are sent again via REST APIs to the third-party VR and AR server that streams, or video server or data server, whatever server, that streams traffic to the user equipment. And then the server incorporates those recommended values. And these recommended values can also be sent to the user equipment, because if the player and the user needs to optimize some parameters for uplink transmission, then this is also sent to the user equipment. And our results have shown that when intelligence about the RAN is sent to the higher layers, it helps improve the performance of latency, throughput, and goodput. One of the use cases talks about optimizing the IP packet sizes based on predicted RAN latency. So as opposed to using the default IP packet size of 1500 bytes, the application server used a packet size of 650 bytes because it was able to predict that the underlying RAN latency was high. As a result, the latency improved by 35%, the throughput improved by 60%, and the AR goodput increased by 50%. This is just to showcase, how you can have end-to-end intelligence based on the RIC and network edge cloud. So to conclude, we spoke about the traditional RAN, disaggregated RAN, virtualized RAN, and open RAN architectures. We also spoke about the interfaces in open RAN. We spoke about how to use machine learning models for optimizing and for making policy decisions in both the non-real-time RIC and the near-real-time RIC, and flows between hierarchical control loops. We spoke about two key use cases. One use case to optimize the cellular RAN functionality. This is a latency-assisted traffic split in dual-connected networks. And then the other use case was how you can actually optimize the end-to-end performance of an end-to-end network by leveraging real-time intelligence from the RAN and by leveraging containerized microservices in network edge clouds. Just a brief about myself and my company. So I recently joined Mavenir as a principal technical architect. It's been less than 2 weeks for me here. My areas of expertise include RAN design and optimization, open RAN architectures, and cross-layer optimization in cellular mobile systems. I've had prior work experience with AT&T Labs, Microsoft Research, xran.org, which was the precursor to Open RAN, Intel Labs, NEC Labs, Broadcom, etc. I finished my PhD in computer science from the University of California at Davis in 2016. And about my company Mavenir, Mavenir is industry's first and only end-to-end cloud-native network software vendor for communication service providers. We are headquartered in Richardson, Texas, and we have a comprehensive portfolio covering all layers of the protocol stack, including the radio, packet core, and applications. We are selected as the ORAN services provider for Dish Network, Vodafone, etc. And we also have quite a bit of accolades that are worth mentioning here, as you can see in the slide. That's it for my presentation today. Thank you, and I'm open to questions.